Okay, dear students. So in this video, we're going to start our new topic, which is E1 and atomic physics. And in this topic, we're going to concentrate on structure of atom. So what are the things that we are going to understand now? The point number one is the Thomson model, which is very small and like it's a very small theory. Nobody's asking you any question from the Thomson model, by the way, but still, it is the part of syllabus. We have to do it. And then the second thing that we are going to complete in this video will be the Rutherford model, without the mathematical aspect of it, without creating any further mathematical conclusions, but only the theory about the Rutherford model. Okay, so Thomson was the first person who created a model of atom and he conceptualized that. But of course, that was really at a very basic level. So, of course, it was not able to stand the test of time. So, Thomson said that atom is, first of all, spherical in shape, which was probably the only right thing. And the atom is of spherical shape and it was made up of positively charged fluid. Positively charged fluid, and it was containing electrons within this sphere, because the atom is overall neutral, so it got to have equal number of negative charge. So what are these electrons doing there? They're just dipped into that pool and they're just moving around, you can say. So that is why it got many different names. Like people started calling it pudding model, then people called it watermelon model, and there's so many different names for this model, because like this is the positively charged fluid and there are electrons inside, just like seeds of watermelon, like that. So that's it in this model, nothing more. And this model is not that very famous in IB also, like they're not asking many questions from this. Anyways, so this is it for Thomson. Let us now move to Rutherford's model. Now, Rutherford and his team, they did some experiment with a gold foil. Sorry for sorry for that. So gold foil. So they took this thin gold foil. Now there are many different kind of students. No, like one of my students asked me that why are they using gold for an experiment? Were they very rich? And there was no fear to damage the gold foil. So very funny, but still, what is the reason for it? Let me tell you the reason. The reason is that gold foil is highly ductile. The gold material is highly ductile material. So you people can, ductile as well as malleable. So you people can beat it into sheets which are very, very thin. So actually, in this experiment, there is one condition which is on the gold foil, that it should be very thin. It's kind of like the thickness of the gold foil is assumed to be one atom thick. Of course, that is not the right assumption, but they do have that kind of assumption. Now the thing is that you have to beat that gold foil in such a way that it should be as thin as possible. You can say that. That is why they have chosen gold as a material, because it is the most malleable and ductile material available with us. Okay, so what happened? Okay, let me explain you the experimental setup first of all. So they were using some radioactive material, which was, to the best of my memory, they can say radium, and it was producing alpha particles. They all were bombarded on the gold foil. And this material, this box is actually made up of lead, and the alpha is not able to pass through lead. So the scientist people, the community, they can stand behind it, so that the alpha radiation, which is obviously the carcinogenic and all, so that should not be able to damage the scientist who is working on it. So this is lead material, which is kind of providing us the safety net. So this alpha is going towards the gold foil and it is hitting here. So there were three different observations they were made. So point number one, the first observation is most particles, they are undeflected and they are going within, like plus minus 5 degrees, or you can say plus minus 10 degrees. You can say some books are saying something, some books have a different data, kind of like overall the deflection is very minor, and this is happening. So this is happening for how many particles? Kind of like 99.9% of alpha particles are able to pass through the gold foil without making any damage to the gold foil and without having any major deflection. So they're just passing through the gold foil as if there is nothing there, like that. So a very small amount of deflection is definitely registered here. That is the point number one. And the books are saying 99.9% of alpha particle are passing like that. Now, what about these kind of deflections? This is the second observation, that a very small number of alpha particle are getting deflected through a very large angle, or you can say obtuse angle, more than 90 degrees. And the value sometimes it is given as 1 in 8,000 alpha particles which are bombarded. It is getting deflected by an angle which is more than 90 degrees. Now, what is the third observation? The third observation is that one or some particle are also getting reflected at 180 degrees back. So, but that ratio is too low. It's kind of like 1 in 100,000 alpha particles, which is getting reflected cent percent. Like it is actually retracing the path from where it was coming. So it is going like that. So that is happening indeed, but that is happening a very less time. This is what is happening. These are the three things, three observations that we can make from the Rutherford's model. But what are the inferences? So what do we learn from these observations? What can we say about it? So let us just imagine that this is the gold foil and there are some atoms which are like this. So the first problem is that majority of the particles are just passing through the gold foil without even creating any serious damage, and nothing is happening. The alpha particle is able to pass through it. How is that possible? So the point number one was there is a lot of empty space inside the atom. So we can say there's a lot of empty space inside atom through which the alpha particle is able to pass through. Because let's say I'm throwing a ball on a wall here, and without causing any serious damage to the wall, the ball is able to pass through it. How is that possible? Well, if there is a window there, if there is a hole there in the wall, clearly the ball is going to pass through the wall. And we will see that, okay, fine, the ball is passing, so there has to be a window. Similarly, we can say that the atom is majorly made up of empty space. Ironic. But what is the second point that Rutherford had created here? So he said that first of all of the particles are passing through it. It means that there are empty spaces around it. So where is not empty space? So you can say, like, let's say there is an alpha particle coming and it is getting bombarded like this. Some of the alpha particles are also retracing their path. So we can say that there is a tiny particle there, a very tiny particle. Why? Because if let's say it is a big particle, let's say it's a very big particle. So why a very small number of particles are getting deflected by large angle? There will be many more. There will be many more because the particle is bigger in size. Obviously, it would be stopping more number of particles from passing through it. But that is not the case, which clearly means that this central particle is tiny. So the first point that I wrote here, right here, is tiny particle at the center of atom. Of course, tiny particle. Now, point number three, it has to be positively charged. Like, why do you think it is positively charged? Because alpha, which is coming and which is getting bombarded here, it is all positive charge plus 2. Positive charge is there on alpha particle. Now when alpha particle is going towards the nucleus, if let's say the nucleus is negatively charged and positive charge is coming, there will be a tendency to actually cling to the nucleus rather than getting deflected. But you can see majority of the particles are able to pass through it without any loss of number of particles. Nobody is clinging to the nucleus. Even you have such particles, those who are getting reflected at a very big angle, which clearly means that the central part has to be positively charged. So there we are. We just assume it that fine, no problem, it is positively charged. Point number four. Now, point number four is that when you talk about the radioactive materials and the radioactive active radiations, you have alpha, beta, and gamma. We would be doing those things in coming upcoming videos in detail. Alpha is actually the heaviest radioactive radiation. Beta is just an electron, far more thinner and far more smaller in size than alpha. Gamma is just an electromagnetic wave. So we thought alpha to be a very heavy particle. Now this heavy particle is getting reflected at 180 degrees. It is getting reflected at very bigger angles. Even then, there is no serious damage caused to the gold foil. Why? Well, this can happen only if it is colliding with a particle which is very massive. Massive means it is having a lot of mass there, and this particle is not able to create any serious damage to the nucleus even when it is colliding head on the nucleus. There is no damage. So it means that the nucleus is very massive. Now, massive doesn't mean that the radius is very big. Massive means mass is very big. It has a very big mass. So that mass is big. So we can say this tiny particle at the center of the atom will be known as nucleus. Now, this is how Rutherford conceptualized the model of the atom. So he said that according to me, the atom is having nucleus here and all space around it is just empty. But where are the electrons? So there comes the point number five, electrons. Now he says that electrons are there because the atom is electrically neutral. There has to be the same number of electrons in the atom. So they are there. So where are they? Obviously, they will be in the empty space somewhere because they can't go into the positive charge. Otherwise, positive charge of the nucleus will be damaged. It means that electrons are somewhere here in this space. What are they doing there? If they're just standing there, the Coulomb force will attract it and electrons will fall into the nucleus. So we have to create a force which is in the opposite direction. So that could be centrifugal, isn't it? Like you remember that in the circular motion that we did in A1. So it means that electrons are moving around in the orbits here with certain velocity. And so the Coulombic force is actually acting like centripetal force there. And that is why the electron is moving in the circular fashion around the nucleus. Okay, fine, no problem. So electrons are there and they are revolving around this. So we can, he was the one who used the word solar system. He said that electrons are actually revolving around the nucleus just like planets are revolving around the sun in our solar system. So he was the one who created these corollary systems, like systems similar to the solar system. So he created this thing. Now, what is the last point that we can make here? Now, the last point, point number six, is anything about the orbits? Nothing at all. So he said that there is no condition on orbit. Electron can revolve anywhere. Well, it depends upon its velocity because the centripetal force mv square by r will be equal to the Coulombic force. And from there we can find whatever radius, and according to the radius, the velocities will be different. So there is actually no condition on the orbits of electron. Okay, so just like solar system, like Earth orbit or the Mars orbit or the Jupiter, there is no condition on the orbit that only in this orbit you can move. They can move around the sun in any orbit, by the way. Asteroids are moving in just damn any orbits, isn't it? Like comet is moving in its own orbit. So there is no condition on the orbit in the solar system. Similarly, he said that there is no condition on the orbits in atom also. So this is it for this video. In this video, we have learned everything about the Rutherford's model theoretically. By the way, after that, there are a couple of things like the distance of closest approach, the estimation of the nucleus radii, and many things. There are some, um, I would say, outfalls because of the like conclusions that can be made from the Rutherford's theory, but we are not discussing them yet. They will be taken later on in some other video. Okay, dear students, so till then, all the best. Thanks for watching.